We're in our next video in number 3, and here we're going to continue our lesson in the theory of congruences. And now we're going to talk about the concept of congruence classes. Okay, so we have talked about this a little bit in the first video in the theory of congruences. I have called this the equivalence classes. Either way, the concept is similar, if not the same. So given an integer a, so let q be the quotient and r be the remainder upon division by n. So this is very similar, or actually the division algorithm, only with different variables, so that we can see that a is equal to q times n plus r. Remember the division algorithm as a is equal to b, or rather b times q plus r. So this is very similar, where r, the remainder, is strictly less than the n, but not really um, strictly greater than 0, so it can be equal to 0. So this is given an integer a, upon division by n, q is the quotient and r is the remainder. Then by the division of congruences, okay, by the division of congruences, okay, we can see here a is congruent to r, the remainder, mod n. Okay, again, a, the dividend, is congruent to the remainder, mod n. Actually, when we are doing, or when we're dealing with with the with the equivalence classes, the remainder is of a very special attention. Okay, actually the one, the b, okay, actually is the remainder there. So a is congruent to this remainder, mod n. That's why some call it as the arithmetic of remainders. Remember in the first video, okay, that we call the theory of congruences, as it is popularly known or commonly known as the theory of congruences. Some again call it modular arithmetic or clock arithmetic, but it's also known as the arithmetic of remainders, okay, as called by Gauss. Okay, so again, let me highlight this: a is congruent to the remainder mod the divisor, because there are n choices of r. We see that every integer is congruent modulo n. This is congruent modulo n to exactly one of the values, 0, 1, 2, up until n minus 1. So um, again, all of the numbers are congruent, or congruent modulo n, exactly to these values. Actually, n is congruent to 0. Okay, so n is congruent to 0, in which I will show in the next part. In particular, um, a is congruent to 0 mod n, if and only if n divides a. Okay, so n is congruent to 0. And rather, a is congruent to 0 mod n if n divides a. So the set of n integers 0, 1, 2, 3, 4, 5 until n minus 1, okay, is called the set of the least non-negative residues modulo n. Or we call this as the congruence classes modulo n, depending on this modulo n. But particularly, we call this as the congruence classes. Okay, or if you want the 0, starting with the 0 up until n minus 1, so this is the least. This is the least. So one illustration, again, I have illustrated this in the first video. I have given an example of mod 7, but let's make it simple now in this video. I'll give you one example of say mod 4 for a start. So for mod 4, we'll start with the number 0. So we're going to, in particular, we're going to talk about all the numbers here. Let's start with 0, 1, 2, 3, oops, 3, 4, 5, 6, 7, 8, 9. Let's stop with 10. Let's try to imagine them in a number line. shall we? Oops, not really a line. Okay, let's imagine that. Let's imagine that it's straight. Now 0, 1, 2, 3, 4, 5, 6, 7, up until any number actually. As this continues on and on. There are different numbers, but when we enter the theory of congruences in the arithmetic of remainders, we are making them equivalent in some cases depending on its modulo 4. So let's start with the particular number 1. Okay, so 1 is one of the first classes, 2, 3, and we stop there because we're stopping with a set of integers n minus 1. Our n is 4, so we stop there. So with 4 is actually congruent to 0. Let me change the color of the pen. So 4 is congruent to 0. Okay, 4 is congruent to 0. And then 5. Think of 5 this time. Okay, think of 5. 5, 6, 7, 8, 9, 10. Let's finish putting tick marks there. Okay, again, think of 5. 5 is equivalent to what number from these numbers here? From these numbers here. What is the equivalent of 5? Okay, 5 actually is equivalent to 1 mod 4. 6 is equivalent to 2 mod 2. 3 is equivalent to 7 mod 4. Or rather, sorry, again, mod 4 again. 4 is equivalent to 0 mod 4. 5 is equivalent to 1 mod 4. 6 is equivalent to 2 mod 4. 7 is equivalent to 3 mod 4. And then we stop there. We can say again that 8 is congruent to 4 and 0. 5 is congruent to 9, and 10 is congruent to 6. All that in mod 4. Now, actually, what we are doing right here, what are we doing is we're creating this number line in a loop, okay, in a circle. We're imagining this in a circle, and this circle is somehow composed of only integers 0, 1, uh, 0, 1, 2, 3. Okay, that is in mod 4. I'm trying to imagine. I don't know. I cannot make a perfect circle. Anyways, okay, let's try to imagine this is perfect. So let's start with 0 here, 1 here, 2, 3. It's like you are imagining a clock that is only has 4 hours. 0, 1, 2, 3. If you want, you can make this 4 here. So we know that 4 is over here because after we go back to 0, after going or rotating from this part of the clock going here, we go back to 4. Okay, or 0. Or I mean when we had 4, we go back around the clock and then we have 0 again. When we have 5, we rotate and we go back to 1. When we have 6, we go back to 2. When we have 7, we go back to 3. When we have 8, we go back to this 4 here. When we have 9, we're here, and like that, because 10 is congruent to 2 mod 4. I think we don't need to do the arithmetic anymore. 10 minus 2 is 8, which is mod 4. Okay. Also, we can verify that 7 is equivalent to 3 mod 4. Why is that? Because 7 minus 3 is 4 itself, mod 4. But to think um, they're the congruence classes. This is one congruence class. This is also one congruence class. This is one congruence class. This is one congruence class. And then I am not restricting you that these are the only numbers, integers in this congruence class, because this goes on and on. This can go on and on. Also here. Actually, it can go on inside. Okay. So for example, if we will have -1, -1 is here, -2 is here, -3 is here. part of the congruence classes of 1. So if we try to imagine, the negative 3 is congruent to, say, let's try 9. 9 mod 4. Why is that? Because 3 minus 9 is going to give us negative 12. Negative 12 is divisible by 4, or 4 is a factor of negative 12. Multiply negative 4 by negative 3. That's going to give us negative 12, right? So this is one example of of um, of equivalence classes. If you want to put them in a list, we can actually. We can. So if you want to list them, we have 0, 1, 2, 3. After 3, we go back to 4, 5, 6, 7. After 7, we go back. Oops. Go back here. Then what we have is 8, 9, 10, 10, 11, and so on. This is one equivalence class. This is one equivalence class. This is one equivalence class or congruence class. This is also one congruence class. And we call this congruence class, this one here, okay, as the least. Or if you want the particular, the technical term, this is the least, the set. Again, the word is above. The set of least non-negative residues modulo n. Okay. I think it's clear that I can say that it's the least, right? So, um, that's the least. Okay. By our definition, again, the least are composed of 0, 1, 2, up until n minus 1. So this is n is 4, so n minus 1 is 3. So this is the least non-negative residues of modulo n. Okay. So um, in general, a collection of n integers. Okay. In general, a collection of n integers. Let's make this again. In general, a collection of n integers, a sub 1, a sub 2, a sub n, is said to form a complete set of residues, or a complete system of residues, which is modulo n, if every integer is congruent to modulo n to one and only one of the a sub k. Okay, so again, a collection of n integers a to n, a sub 1 to a sub n, forms a complete set of residues, or a system of residues, modulo n, if every integer in that set, okay, in that collection is congruent to modulo n to one and only one a sub k, one and only one of the a sub k. So if you want one example, I can show you one. Actually, for example, here. Okay, for example, let's consider this set composing of negative 12, negative 4, 11, 13, 22, 82, and 91. So we say that this collection of integers constitute a complete set of residues modulo 7 with respect to modulo 7. Why is that so? Because a negative 12 is congruent to 2 mod 7. We can check that. Negative 12 minus 2 is 14. Negative 14, which is indeed inside our definition. But notice that it is congruent to 2. Negative 4 is congruent to 3 mod 7. Again, negative 4 minus 3 is negative 7. That's okay. 11 is congruent to 4 mod 7. 11 minus 4 is going to give us 7. That's okay. 13 is congruent to 6 mod 7 because 13 minus 6 is 7. 21 is congruent to 1 mod 7 because it's going to give us 21. 82 is congruent to 5 mod 7 because it's going to give us 77. And 91 is congruent rather to 0 mod 7 because 91 is directly divisible by 7. 13, correct? 13 times 7 is going to give us 91. So notice, why do we call this a complete set of residues modulo 7? Because negative 12 is congruent to 2, negative 4 is congruent to 3, 11 is congruent to 4, 13 is congruent to 6, 22 is congruent to 1, 82 is congruent to 5, and 91 is congruent to 0. Now, all these integers constitutes the definition 0, 1, 2, 3, up until n minus 1. Our n is 7, so n minus 1 is 6. So we have here the 2, or rather, let's start with 0. Okay, we have here the 0, we have here the 1, we have here the 2, we have here the 3, the 4, the 5, and the 6. So, yeah, therefore we can say that it's a complete set of residues modulo 7. Okay, I mean this collection or this set of integers is a complete set of residues modulo 7. Okay, so if you want one example, okay, if you want, okay, let's have one more example, a very simple one. Again, let's use rather, maybe we can use another mod. Let's make it simple. Let's try mod 3. Okay, this is an exercise. Maybe you can create or imagine a set of integers wherein we can call it a complete set of residues. Okay, or a complete system of residues modulo 3. Okay, go. Okay, do you have now in mind? Okay, hopefully you have now. So let's try. Actually, what we're looking for is something. You can imagine it as like this. Something is going to be congruent to 0 mod 3. Something, another something is going to be congruent to 1 mod 3. Another something is going to be congruent to 2 mod 3. Then we stop there because we only go until n minus 1. So n minus 1 is 3 minus 1 is 2. So we stop there. So we can fill in this. So actually we can fill in a lot of numbers here. Any number will do, provided it's congruent to 0 mod 3. So by the definition in a while that I have shown, um, a any number a is congruent to 0 mod n if n divides a. So therefore, this should be exactly a multiple of 3. So if you want one example, any multiple of 3 will do. Let's try 9. Okay, 9 is congruent to 0 mod 3. Okay, how about for 1? Okay, what number? Maybe we can think of it in this way. What number will that, if you're going to divide it by 3, it's going to give you a remainder of 1. What number, again, will give you a remainder of 1 if you divide it by 3? Any number will do, actually. Think of the number 4. 4 divided by 3 is going to give us 1 remainder 1. Okay, and then we can verify that it's true. 4 minus 1 is 3. So it is okay in terms of our definition. How about 2? What number divided by 3 will give us a remainder of 2? So maybe we can think of the number 17. 17 divided by 3 is 5, remainder 2. So yeah, so meaning this set of numbers, maybe we can put them in order. 4, 9, and 17, okay, is what we call or constitutes a complete set of residues or a complete system of residues modulo n, or complete set of residues modulo n. Okay, so I hope you understood now what we say when we mean congruence classes or equivalence classes. Okay, we have also talked about the set of least non-negative residues modulo n. We have also talked about the complete set of residues, okay, modulo n, or the complete system of residues modulo n, and we have revisited actually the division algorithm for that. Okay, so that's it for this video. Thank you very much for watching. I hope you would like and subscribe. Okay, thank you.